So today we're going to talk about stochastic gradient descent and how we apply gradient descent onto data. So we'll take the things we saw the last couple lectures about gradient descent, which was presented as more of an abstract method for just minimizing a function. And we will show how when we apply this to a version of regression that we can actually so apply gradient descent, and how everything the last kind of 6 or 7 lectures will all connect together. Is there a question? Yes, every time we have a quiz, and what I was about to say, we have quiz 4 today, and as usual, it will cover the last 4 lectures, starting with cross-validation. Okay, every quiz we have will cover the lecture on the day it's given and the previous 3 lectures, unless otherwise specified for like the first quiz. Okay, yes, so it will cover today's lecture. And then we will start the unsupervised learning section, dimensional reduction and clustering after string branch. All right, so your notes used for the quiz should be start with cross-validation. That'll be important. And then the stuff on gradients and gradient descent. That's what will be covered. Okay, just a reminder, homework 4 is posted. Okay, this is, it's on the website. We posted links on Canvas and everything. This is traditionally kind of the trickiest homework. There are 2 parts to it. The first part, it should be pretty straightforward, gradient descent. You should be able to use the Colab file I created as a starting point. Should be fairly straightforward application of what you saw. The second part is applying gradient descent onto data, and will kind of be, you'll have to put a bunch of stuff together over the last kind of 2 sections to kind of understand it. Hopefully it's pretty step by step, but it'll be kind of the most sort of actual Python code you have to write, and you'll actually see how stuff fits together. But what you will be doing and what we'll be seeing today is kind of really the very, very basic version of how like all of like supervised learning actually works in practice. We're going to have a data, turn this into a loss function, then we'll use gradient descent to find the minimum of the loss function. Okay, and you'll get to do this on this fairly simple example. Okay, all right. That's great. So we have a short lecture today because there's the quiz. We'll stop by 4 o'clock. So let me get into it. All right. So we're talking about kind of gradient descent. Right, and we've been talking about for a function that goes from RD to R. Okay, and with this, remember our goal was to be able to use this algorithm to find the argmin of the parameters alpha and RD for this function. Okay, and so today we're going to connect this to data, where now we're going to say that our input, right, is this data x, y that we've been talking about in the section on regression. Okay, and remember, this is these pairs, x1, y1, x2, y2, ... up to xn, yn. And these are going to be in RD, or it's a subset of RD cross R. We are going to kind of work through an example today where, well, so let me just, yeah. So in general, what we're going to develop is going to be called a loss function. So this is a loss function. This is often written as L that takes in this data and some model parameterized by alpha, right? So on here, right? And so what we want to do is set this equal to our f of alpha, right? Where we're going to isolate these parameters alpha in the function, right? It's this loss function that's going to take this in, but we're going to isolate this alpha here as what we're optimizing over. These are the model parameters, okay? And the data is given to us, but this is the input. This is not something we're optimizing over. This is given to us, it's fixed, right? And in particular, we are going to be focusing on the sum of the squared errors. Okay, and so this is going to look like, that means that our loss function f is going to look like a sum over xi, yi in this data set of the model's prediction at xi minus yi squared. Okay, and so again, here is the only thing that's kind of that we're optimizing over is the choice of the alpha. Okay, and so this, because so much uses sum of squared errors, we're going to focus on this, and we're going to kind of derive what the gradient and everything will be in this case, so you don't have to rederive it every time you calculate it. It'll have a very nice form here. Okay. In general, this will be kind of like a dot product, but this could be like a different model that we plug in here. And there are a whole bunch of other models for regression beyond what we talked about in this class. Okay, but they all have parameters, and we want to be able to write down the gradient for these. And it will have a pretty nice form as long as we're using the sum of the squared errors. Okay, and we'll be able to write down this function f and its gradient, and they'll be able to operate on it. And we will be able to do something called stochastic gradient descent, which is what most kind of machine learning uses in practice. Okay, so we'll see what that does. But I need to start from this formulation in order to define stochastic gradient descent. Okay, so in order to walk through this, we're going to focus on an example. It's that blue line. Okay, and an example here where my model M alpha is going to be for polynomial regression. Okay, and we're going to say when d is equal to 1, so that means that my xi is going to be in just a real scalar value. And we're going to look at the case equals p equals 2. Okay, so we're going to work through for this example, and this is a little bit more illustrative than what goes on with just linear regression. But I think we'll pretty much explain what was going on by understanding. If you understand this example, you should be able to generalize to quite a number of other things. All right, so that means that in this case, our model at some value xi, okay, is going to actually just be is just going to be a dot product with alpha and 1 xi squared, right? So I did the expansion of xi. I took it to the 0th power. I got a 1. To the 1st power, I got xi. And to the 2nd power, I get xi squared. And now it looks like this linear regression model. And I already have the 1 in front, so I don't have to worry about the offset, right? So this looks like alpha 0. There's hidden times a 1, alpha 1 xi plus alpha 2 xi squared. Okay, and remember our alpha is now in R3, right? Yeah. Alpha equals alpha 1, alpha 0, alpha 1, alpha 2, right? So these are going to be the parameters, and we're going to want to write down a function f that depends on just these parameters. right? Once we have that function f, we can run this gradient descent step where we iteratively do alpha gets the old alpha minus some learning rate times the gradient at that value alpha, right? So we want to run gradient descent now on here. So we need to be able to figure out what is going to be the gradient. So the key thing we need to do here now is to figure out how to calculate what is this gradient function. Then we can plug it into gradient descent and optimize for alpha. And then even if we don't have that closed form solution that we talked about earlier, we can still optimize. And then this will generalize to a bunch of other problems. Okay. And in practice with stochastic gradient descent, it'll actually run faster than the closed form solution in some cases. Okay. Okay, so in order to define the gradient now, that means that we need to define, in particular, this d alpha j for f alpha, and we need to do this for j equals 0, 1, 2, for all choices. So for j equals 0, 1, or 2, right, we have to be able to define this, right? And so let's write what this down is in this case. This is d alpha j, and this is m alpha of xi. And let's write this. We're going to write this down actually instead of the sum. Let's consider the case. Consider the case where n equals 1. Okay, so we're going to start with this case. Okay, so we only have one data point, so I don't have to write down everything about the sum. Okay, so that means that this term is just a 1 here. Okay, so I don't have to keep track of the I. I have a 1. That's not the index into its coordinate because I used kind of the polynomial regression. I don't have multiple kind of subcoordinates of this, but this is times y1 squared, right? So I need to take the derivative of this, right? When I only have the n equals 1 case, this is my whole loss function, and I need its the derivative with respect to just the alpha j coordinate for j equals 0, 1, or 2. Okay, and so one way of taking the derivative, I have some function that I squared. And so one way of writing the derivative of this is to write it as, I can pull out a 2 times the function. Okay, then times the derivative of alpha x1 minus y. Okay, with no square. Are you able to see that? Let me try writing this a little bit more carefully. Okay, so I've decomposed this term because I have the square here. I pull out the 2. I pull out the value of the function, and then I have the derivative of it. Okay, so I can do this step. There are other ways of deriving it, but this will give us the form that we want. Okay, and then okay, I can write this as 2 m alpha x1 minus y1. Okay, and then I'm going to write out the form of what this function is for polynomial regression. Okay, this function is going to be the sum over j equals 0 to 2 alpha j times x1 to the power j minus y1. Right, so now I've expanded what the model is. I've written it as just this sum here. And now I need to take the derivative of that with respect to alpha j. And what we see is that this should actually be pretty simple, right? It's a sum over a bunch of terms. One of those is a constant, that's y1. And then all the other terms have one of the alpha j's, maybe not this one. Let me change the index of this here, so this is more clear. So I equals 0 to alpha I, right? So there, only one of those matches where the alpha I matches j, the one I actually care about here. Okay, and so then the derivative of it is going to be straightforward, is going to be 2 m alpha x1 minus y1 times x1 to the power j. Okay, the one where it matches, the alpha matches the thing I'm taking the derivative of, is just x1 to the power j. Okay, all the other terms, the derivative is 0, and these go away. Okay, so I've done it. I've written down the partial derivative for just for each of the terms, and it looks pretty simple here. Let me write this up on the next slide. Okay, we're able to write the partial derivative this way. And so what we're going to get is that d alpha j of f of alpha is going to be equal to 2 times alpha x1 minus y1 x1 to the power j. Okay, and again, this was for the case where n equals 1, right? So we were restricting to this case so far. Okay. So this is nice. So now I can write down that the overall gradient f of the gradient f of alpha is going to be d alpha 0, f of alpha, d alpha 1, f of alpha, and d alpha 2, f of alpha, right? So that's the gradient. It gives me a vector, and this is equal to, well, I can factor out this m alpha x1 minus y1 times, so this term here is a scalar. Okay, and then I'm going to get the vector 1 x1 squared. Okay, so sometimes when people write down the loss function, they'll write down a 1/2 in front of the sum of the squared errors, and when you do that, this constant factor 2 goes away. Weird, you get a 2 in front. They say, I really care about the gradient, not the function, so I'll put a 1/2 in front of the function so I don't have to worry about the 2. Okay, cool. What we end up getting here is something nice where I have something that basically records what the data is in the vector. This is the data point, right? So this is basically the data point once I did my polynomial expansion. And then the red scalar part, this is the error or the residual at x1, y1. Okay, so I just calculate what is the residual, and I multiply it by the data points. Okay, so now the gradient turned out to be pretty easy in this case. Okay, this particular form is called the least mean squares so update rule, and sometimes called the Windrow-Hoff so update. Okay, so it has this nice form. So to calculate the gradient at any one point, any one data point, I just calculate the error at that data point, and I basically write down what times the vector of the data point. So calculating the gradient is basically what I have to do is calculate the model, evaluate the model at the data point, measure the error from what I predicted it to be, right? This residual, and multiply it by the data point. Okay, so all we had to do with the gradient and that little bit of practice we had to do, if we use least squares, the gradient's super easy. At least for one data point, yes. Okay, great. Okay. Okay, so this was for one data point. So we'd like to think of, I'm going to call this actually F1, right? So this will be F1 that corresponds, this is F1 corresponding to one data point here. Okay, where I only have one data point. And so in reality then, we want to work with f of alpha, which is going to look like the sum over I equals 1 up to n of f of I alpha, right? So now my loss function, if I do the sum of the squared loss functions, I wrote down the squared loss function for one data point, but now I have n data points. I just sum all of these up. Okay, so now we're in the n greater or equal to 1 case. And then this is called a decomposable function. Okay, and the decomposable refers to that I basically have, I can write down the rule for one function, f of I, for one data point, right? Remember, this is for one data point, xi, yi, and now to get the full loss function, f is now my loss function, it's just the sum of the loss function for each of the data points. Okay, so this decomposable function, whether or not it's a squared error, it could be non-squared error, can still be decomposable, but it's often the sum of all of the data points. This is derived from, we assume that they were independent, and then we wrote down this kind of overall likelihood function, which was the product of each of them, the likelihood of each of the data points. But because they were independent, we can do a log transform, or we can multiply them together, and then through a log transform, we get a sum. Okay, if you remember all that from the first part of class. So this is very common to get these decomposable functions as the loss functions we want to optimize. It's the sum of the contribution of every data point towards how well the model fits, right? So in this case, again, it is fi of alpha, remember, is m alpha xi minus yi squared, right? And so, and this looks like alpha 0 plus alpha 1 xi plus alpha 2 xi squared minus yi squared, right? So this is our running example with the polynomial regression of degree 2. This is an example that we've been working with. Okay, and now we want to use the property that if each fi is convex, then we're going to have that f equals the sum over I of these fi's is also convex. Okay, so when we talked about convex functions, we have the property that if you take the sum of two convex functions, it's also going to be convex. Well, we're going to inherit that here. So if our original function f I of alpha for one data point is convex, then our sum of them, sum of squared errors, will also be convex. And with convexity, we'll be able to run gradient descent and kind of guarantee that the solution we get to, if we ever get there or get close enough, is going to be kind of the global solution. We're going to find this argument. So this is what we want. We want convexity. So let's look at this function here and say, is this going to be convex? What does this function look like? Importantly, is this convex? Can we run gradient descent on it and hope for a good result? Okay. Probably it's going to be convex. Otherwise, this would not be the function of choice. But let's kind of see slightly about that. So let me look at a slightly simpler example, and I'm going to try and draw a picture to explain the convexity of this. Okay. Let's look at the example of M alpha of, why am I getting these extra lines on here? M alpha of xi is just going to be alpha 0 plus alpha 1 xi. Okay, so now we're in the case where it's a linear function or a polynomial degree 1. Okay. What's nice about this is now I can think about my function f in terms of alpha. Now the dimensionality of alpha is 2. It's not 3 anymore, right? This example and before alpha has 3 dimensions. I can't draw a 3-dimensional picture very well, but I can draw a 2-dimensional picture. Okay, so let's see kind of what this looks like. And now we're writing in the alpha space. Oh, this one is going to be alpha 0, and this one is alpha 1. These are the 2 axes we have here, right? So now it'll look like the pictures we plotted last time. I want those pictures to be convex in the space of alpha. Okay, but how do I imagine this with respect to one of the data points here, right? So I'm going to have this equation, I'm going to, for xi, or let's say x1, y1, I'm going to have an equation where I want y1 is approximately alpha 0 plus alpha 1 x1, right? So I would like to have this property here. And I'm going to have, if I have it so it's equal, if I'm going to have that so this equation is equal, then my error on this data point is going to be 0, right? It's going to have no error. So that means that my model is going to equal what this prediction is. What is the space in alpha land, right? This 2-dimensional space of alpha, where that equation is 0. What does that look like? What does that look like? Well, so I think I want f of alpha equals to 0 if we're going to have alpha 0 is going to equal to y minus alpha 1 x1. Right? So what does this correspond to? It's going to kind of correspond. This now I can write this as an equation of alpha 0 as a function of alpha 1. This is going to kind of look like a line in this space. Okay, so this will be the line where alpha 0 is equal to y minus alpha 1 x1. Right, so this line corresponds with the 0 set of our function. Okay, and then I can imagine, I can imagine now that I have a so that it should, maybe it doesn't quite make sense where the line is, but you should kind of believe it's a line, right? This looks like the equation of a line, but now I've swapped the roles of x and y with alpha 0 and so an alpha 1. Okay, and what's going to happen is that as I deviate from this line, my cost is going to increase. How much I'm going to deviate, and so I'm going to get some kind of deviation, and the amount I deviate is going to give me a residual. I'm going to square this residual, so I'm going to kind of give this this function, which looks like this. So if you're a fan of like Chloe Kim, right, this is like a half pipe. If I were, it's a little bit hard doing the best version of drawing this, but think of like there's a half pipe, and the bottom of the half pipe is this line here, and it's curving like a parabola up. Okay, so this is what the loss function looks like for, this is what the f of alpha function looks like for one data point. It will look like a line at the bottom and then a parabola curving off the line. Okay, is this function convex in the space of alpha? What do you guys think? Some shaking heads, no. Okay, how do we check if it was convex? What we did is we took two data points. These were projected. These are in the alpha 0, alpha 1 space, but this is P, alpha 0, P, alpha 1 of P, right? And then there was another point here, Q, right? And this was, and then we lifted, let me put, right? And we lifted them up onto this function. Okay, so they live on the plane, and then we lift them up under the function. And we want to say, well, if I consider the function value at these 2 points, and I'm going to compare that to the straight line in between these values, is the function, if it's convex, the function, the yellow function here with the green minimum needs to always be below the straight line, purple straight. Then if that's true for every choice of P and Q, then this is going to be a convex function, less than or equal. Okay, so if I pick 2 points on the same piece of parabola, that's going to be true, right? It's a parabola, just a one-dimensional curve. If I pick them on different parabolas, like in a half pipe, I could think of have a string going between 2 points on the half pipe, and it stays above the snow, right? This is when they're, gain some air. Usually don't do that in the middle, but okay, but it's okay, that's going to be convex. What if I picked 2 points, say P prime here and Q prime here? Is this going to work for this point? The height of those 2 points is both 0. So is the line here staying above or equal to the function value? It's equal, so it's okay. It's as long as it's not below, it's okay, right? The half pipe is nice and curved, smooth, looks like a parabola, but it's kind of stretched out along a line. This is convex, okay? This function, F1 of alpha, is convex, okay? Is it, okay, so it is convex. You believe me? Okay, hopefully, okay, good, great. I like the audio response. All right, is it strongly convex? Remember what strongly convex means? What does strongly convex mean? Yep. Yeah, so right. So you're thinking of, yeah, so if it's strongly convex, it's going to be, the function can fit between two parabolas. This is great. We had another definition of strongly convex earlier, which is, so you can understand it through this definition, but there's another definition from the first lecture on functions. What was that? So sorry, strongly convex, you're totally right. Is it strictly convex? Yeah. Is it, remember what it means to be strictly convex? Yeah. Yeah, it has to be strictly convex is when I had this, the purple line needed to always stay above and never equal to, except on the endpoints. Okay, the strictly convex. In order to be strongly convex, it has to be strictly convex. Okay, these 2 points are not. This demonstrates it's not strictly convex because the midpoint is on the function. Okay, so along the bottom line, and in fact, any pair of points parallel to this line are not going to be strictly convex. Okay, so it's not strictly convex. I cannot fit a parabola that goes underneath this red curve, this red segment. I can't fit it underneath without being totally flat. So I can't get the strong convexity. I can't get the fast convergence. Okay, yeah. The whole function has to satisfy this for all P and Q to be strictly convex. So if I looked at one slice, most of the slices, except the one parallel to the green line, are going to be strictly convex, but I need to hold for all P and Q.
So then I guess my next question is, why I thought it was too much P above beyond line and also P below.
So will P and Q live in the alpha, is this, in the alpha 0, alpha 1 plane? And then I look at the point, the D plus 1 dimensional point, where I look at the alpha coordinates and then the D plus 1 coordinate of the function. Right, and I'm looking, and so that this line segment needs to stay above, not the part on the plane.
It needs to stay above where?
This orange function value, which is defining the half pipe. This purple line segment.
Oh,
so these 2 points are on the half pipes, right? And then this is a string inside the half pipe, right? And that stays above. Okay, but if I'm on the base of the half pipe or anything shifted off here, it'll stay exactly on it. And so I don't get the strict or the strong convexity or my fast convergence. Okay, so this seems not great. For my linear regression, you know, Grainta said, I wanted to get really fast convergence. I kind of promised this to you, but I haven't gotten this yet. But we only looked at one data point. Okay, so I can fix it by looking at another data point. If I sum up things, if I look at only one data point, I don't get strong convexity or fast convergence. But if I look at another data point, let's say, if now I have data point x2 and y2, it will correspond to f of 2 alpha equals 0 will correspond to alpha 0. This was alpha 0 equals y2 minus alpha 1 x2. Right? So now I have another data point. This will going to give me another line here. And through this line, I'm going to get another kind of half pipe. Right? I'm going to get another half pipe through here. This second line with the second data point, this is going to correspond with alpha 0 equals y2 minus alpha 1 x2. Okay, and so this line will also be convex, but not strictly or strongly convex. But now if I combine these together and I add them up, okay, there's only one point where they can both be 0, right here. This point, they can both be 0, and in every other direction, one of the 2 functions is going to look like a parabola. Okay, and so the sum of 2 of them in this case, as long as they're not degenerate in some weird way, they aren't somehow parallel lines to each other, these are going to be strictly convex and strongly convex. Okay, so in general, if I have enough data points, enough at least D data points for D-dimensional function, and they're not in some really weird configuration, I'm going to get strong convexity. And then I'll get really fast convergence. Okay. Okay, so then I'm going to get that the sum of Fi is usually, almost always, right, usually strongly convex. So then I'm going to get super fast convergence with my gradient descent. Yeah. Yeah, so let me, okay, so now that I've drawn them on top of each other, it gets a little harder. There's a picture in the textbook which has just one and then both of them, but it's the same picture. So so think of, can you imagine the picture of the half pipe that has a 0 along the bottom, and so I don't get strong convexity. If I'm on here, I don't know if there's a lower point someplace. Okay, and now I have another function that's this way now. Think of, there's another half pipe, and now I take the average of the two half pipes, right? So if I go in this direction, it's going to be the yellow one is getting larger very quickly, even though the blue one is flat. And now if I go along this green direction, the blue-black one is kind of increasing. So if I move away from this point along the green direction, before it was just this function is flat, but now the blue and the black function is kind of increasing along this. So in any direction I go, I get some component which is going to be kind of decreasing with the residuals are increasing, and so then the squared residual is increasing like a parabola. Okay. Yeah.
So it works because they're particular, so they're strong complexity to it. Because all if you were to P1 to P1, it is part of the blue.
Yeah, they don't have to even be perpendicular. As long as they're not parallel, it works. Okay, I will be able to get the eta in the strong convexity. The eta strong convexity will be larger the more perpendicular they are. But if I'm putting like 10 or 20 or 100 data points, I'm going to have most of them in any direction are going to be kind of give me this parabolic function that I'm averaging over, and I'll get like it'll look like one. The whole function is really going to look like just one parabola. What? Okay. All right. Okay. So I have a couple more important things to say before we get to the quiz. So now we can talk about the gradient descent. Okay. Gradient descent here. Okay, and again, we're doing alpha equals minus the learning rate times the gradient, which we now know how to compute. And we're going to look at the case where n equals is large. Okay, and so we can write down and so we will, in this class, to distinguish it, we'll call this batch gradient descent. Batch sometimes refers to a subset of all the data points, but still more than one thing at a time. Okay, and so we're going to have the gradient f of alpha equals the gradient of the sum 1 of n of f of I of alpha. And it turns out the gradient is linear operator, so I can push this through the sum. So the gradient equals the sum of the gradients of these fi functions. Okay, so that means that now my d alpha j of f of alpha is going to be sum of I equals 1 to n of d alpha j of f of I of alpha, and this will be 2 times the sum of I equals 1 to n of the xi minus yi squared times xi to the j. Right, remember we had derived through this least mean squared update rule, the Windrow-Hoff result, that we could write down the gradient in this way, and now it's the sum over the sum of the squared errors, but I multiplied the sum of the squared errors times the the value of the data point. Okay, and so now I can write down kind of in general, f of alpha, the gradient of f of alpha is 2 times I equals 1 to n times I only have to calculate this once per data point, even if it's multidimensional, times this vector, right? So I can compute the residual once, and I multiply it times the vector, right? So the calculation of the gradient is pretty straightforward. Okay, it's just evaluating the function, measuring the error, multiplying it by the data point, adding this up, and then there's a 2 in front. Okay, so this would be gradient descent on here. Okay, the problem and the reason people like this is data sets have gotten very, very big. And so to calculate the gradient, I need to spend linear time. I need to review every data point to calculate the gradient. And if I have a billion data points, this is really slow. I need to take lots of steps. I don't want to look at every data point, every step. Okay, so what is typically done instead is what's called incremental gradient descent. Okay, so incremental gradient descent instead says it's going to use the approximation is going to be about, on average, I can use the gradient defined for any one data point as an approximation of the gradient. Okay, so this is not the right gradient, but I should be able to compute this term much faster than I could compute the gradient for the full gradient for all the data points. Okay, so now I will start alpha 0, my initialization. So I will set I equals to 1, and then I'm going to repeat where alpha k plus 1 is going to equal to alpha k, what I had at the kth step, minus the kind of learning rate, which maybe I adjust, maybe I don't, times, and only using the gradient, the ith gradient here. Okay, I will update I in the next step equals I plus 1 mod n. Okay, so once I get to the nth data point, I want to loop back to the first one again. Okay, so I increment the data point. So every step I look at the next data point in order, and I use that to estimate the gradient. Okay, and I do this until, let's say, the norm of the gradient of the kth gradient is less than some threshold here. Okay, and then I will return alpha k. Okay, so there's a problem. So I just estimated the gradient with using just one data point every step. This is much faster. Okay, it takes constant time to estimate the gradient, but it's noisier. It's not the right direction to go, but it's kind of close. A problem is this rule for when to stop is now noisy. Okay, so this now is noisy. This is a noisy judge. So I need to average over, say, 10 steps. I can no longer use just one. It's not always decreasing. I might have one, like an outlier that says it's really big, or it's 0 for one of the points. I fit it exactly. Doesn't mean I should stop. I need to make sure on average it's small. This is now a noisier thing to do, so I need to take an average here. Okay, so this is called incremental gradient descent. Okay, what's commonly called, and what the title of this lecture is, is called stochastic gradient descent. Okay, and so this is what everyone claims to use in they usually don't call it incremental gradient descent. They use stochastic gradient descent instead. This is basically the same thing, except stochastic means random. Okay, so you can kind of guess that I start out the same way. So I start with some guess of my alpha parameters, then I repeat, but now I'm going to choose some I in the set of all possible kind of elements, one dot 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 n. So I choose one of the data points at random. Okay, and then I will do the same thing. Okay, minus the learning rate times the gradient now at this random choice of some data points. Okay, and again, I do this until I have that the gradient at fi, the norm of this gradient is less than some threshold, then I can probably stop. And again, I need to take an average here to trust this. Okay. And finally, I will return, if I decide to stop, then I will return the parameters at alpha k. Okay, so this is stochastic gradient descent. And so this is what everyone claims to use. In practice, a lot of times you actually use incremental gradient descent. You just walk through the data points in order. The step here of choosing a data point as random is slow for a couple of reasons. One, if I'm doing calculations, a lot of these calculations are pretty straightforward. It can be done fast. Choosing a random number is a relatively slow operation. This piece of code is like the core, the very bottom basic of a lot of these optimizations. So they want to make it as fast as possible. Choosing a random number would dominate the cost of this internal step. So they don't really want to do that. The other reason why you don't want to do it is not only do you have to choose a random number, but we're not really working in like the RAM model here, where it takes, you don't have random access to all the data. You have a really, really big data set. It's probably on disk, okay? And you need to read it into memory. To choose a random one, you need to go pull it from disk into memory, and that's even worse, okay? So typically, in practice, what you do, although the analysis, you can prove stuff about stochastic gradient descent, it's harder to about incremental, but you would randomize the order, and then you would run incremental gradient descent. So then once you have randomized the order, I do that once, and then I can just read stuff and I can do prefetching, and I don't have to do that. All right, last time it was coyotes, okay? He was howled at by coyotes, but I will, hopefully his mom can handle it. Okay, so hopefully he doesn't get eaten by coyotes also. I looked it up, they're not too dangerous here. Okay, so the last thing before we take the quiz, when you're running stochastic gradient descent, you should think of, you have this function that you're trying to get to the minimum of, and you hope this is convex. With gradient descent, you're going to keep going down. This would be gradient descent. With stochastic gradient descent, it's going to be noisier. And so sometimes the score increases. So this would be SGD. So you typically will take smaller steps, not that much smaller, but maybe 20% of the size of steps, but each step is much, much faster. Okay, and overall, it's a big win. So this is what everyone uses. You're going to get a noisier path down, but on average, it's going in the right direction. Okay, one last question, then we'll take the quiz. Gradient descent, if you remember from Monday's lecture, there's this function and we're walking down that function using the gradient. And that's what these waypoints are doing. We plotted it. You'll do this in your homework. And the gradient descent keeps going down. The stochastic gradient descent might go back up a little bit because it's an error in the estimation of the gradient function. Okay, great. Let's finish up making your notes really quick, and we're going to start handing out the quizzes. Remember to put all your cell phones and calculators and stuff below the desk, and try not to sit directly next to each other. Spread out just a little bit. You can start when you get the quiz.